So, good afternoon, everyone. I would like to thank you again, Roberto, for introducing so nicely this topic. I think, in addition to the fears and to the good direction of big data, there is a third direction, which is science. And science is driving this field very strongly because basically we want to answer basic questions that require incredibly large infrastructures. And what are these basic questions? Fundamental physics, the field where I come from, is really after how did the universe begin, and what is the destiny of the universe, and what are the basic components of the universe, and what are the fundamental laws of the universe. And all those questions require very large experiments nowadays, because we have basically finished the era where scientists could build something on the tabletop and come to results. We really started already 30 years ago, an era where fundamental questions like this one must be answered by very large collaboration and multinational enterprises, which come together at funding level and organizational level and put something which is unique in the world. So two examples that I'd like to bring here is at macroscopic level and microscopic level are the TMT and the LHC. So the TMT is a 30-meter telescope, which is not realized yet. It's a project that is in the scale of 2010s and will be the largest telescope ever realized. On the other end, you see the LHC, which is the largest particle accelerator ever realized. And they give you the feeling of the scale at which we have been doing science now to answer the macroscopic questions, so how the universe works at macroscopic level and at microscopic level. So how does the fundamental particles that build the universe interact to each other, and what are the building blocks of nature? So now, how do these two fields complement each other? The problem with the optical telescopes, or with radio telescopes, or with the microwave, is that you hit the wall. And if you go back in time, the farther you look with the telescope, you go back in time, you hit the wall at about 13.8 billion years. And you don't see beyond this wall. You just see the microwave background, which is the frozen state of the Big Bang. You don't see anything beyond that, but we want to go beyond that. So what you have to do is to realize the beginning of the universe in a controlled environment, basically. And that's what we do at the LHC. So this is another view, if you want, to explain what's going on here. You have a history of the universe that starts from the Big Bang up to nowadays. So you see mankind here, and all the steps in between in terms of time, in terms of temperature, and in terms of energy here. So with the telescope, you can go basically up to the first 300K years here, and you hit this wall. You cannot go below that, and you see only the cosmic microwave background. But you want to examine what's going on here. What are the building blocks? How do they interact with each other? How do they froze down? How were particles formed? How were protons and neutrons formed? How were the atoms formed? Okay, to answer all these questions, you have to go beyond that wall. So this is why we use particle accelerators, because we can reach the energy levels that can basically access this instance of the universe that were 10 to the minus 10 seconds after the Big Bang, okay? So also, at the LHC, we also try to study the nature of condensed matter and how particles were condensed into protons and neutrons, and how the atoms were formed. So after the first 3 minutes, you see that neutrons and protons are forming a nucleus, for example. Okay, so this is also a process which is beyond the wall. So how do we break that wall and study the early universe? And the answer is particle colliders. Particle colliders are this control environment which I mentioned right now. So you have two beams of particles. In this case are two protons, and each proton is made of elementary particles that we call quarks. What you do is that you accelerate these particles to very, very high energy such that when they interact, you basically have an interaction between elementary components of the protons. So two quarks interact with each other. And when they interact, the energy, the budget of energy that you're putting into the system can be converted into other particles, okay? This is the famous Einstein equation that you typically see. Usually people show this part of it, but this is true only when things are produced at rest, so when things don't move. But we produce particles that move, so you have to, the initial energy budget is converted into the mass of the particles that produce plus the momentum of the particles that you produce. So what we are interested in the mass, because we want to produce particles that were existing only in the initial phase of the universe, of unstable particles that are very heavy and that are not ordinary matter of which me and you are made of. So in order to do that, the Large Hadron Collider was built. This is a very large particle accelerator. It's with 27 kilometers of diameter, and of circumference. And there are two very large experiments, very large collaborations also, that were put in place to study the interactions between protons. I've been working for CMS for over 10 years, and the other experiment is Atlas. So this is a picture of how the underground area looks like. You have 27 kilometers of dipole magnets here. All of those the beams are circulating in these pipes, but these are not normal pipes. These are pipes which are operating at cryogenic temperature of a few Kelvin, so 1.7 Kelvin, which is, so you can imagine that you have liquid helium over 27 kilometers circulated in this machine, which is a challenge by itself. The Large Hadron Collider, you see, it's located at the border between Geneva and France, okay? And this is the Geneva airport here, so Accenture is over there somewhere. And what you see here is the representation of the ring, which is sitting 100 meters underground. So, as I said before, the accelerator is not enough. You need to take pictures of the interactions, and this is why you need these particle detectors. So that's why I've represented here a photo camera here to take the pictures of the interaction which are happening very, very frequently. But how frequently? This is how, for example, the CMS detector looks like. This is compared to the scale of a person. And the two beams are coming from the opposite sides, and as the particle collide in the center, you will have all the particles coming out from the interactions, and the various layers of the detector are there to measure the direction and the energy of these particles, okay? So a few numbers here. The total weight is about 14,000 tons, which is heavier than the Eiffel Tower, and the overall diameter is condensed in 15 meters with an overall length of about 30 meters. Another nice characteristic of CMS is this as the largest solenoid on Earth. It's with a diameter of 5 meters, and it produces a very large magnetic field of 3.8 Tesla. Now, this is where the big data aspect comes in. We are taking pictures 40 million times per second. And we are storing 300 to 600 megabytes per second of data, because we are looking for very rare processes, so we have to produce billions of collisions in order to get one good collision that has produced the particle that we want, that we are really looking for. So, for example, a few years ago, we discovered the Higgs boson, and as a part of this project, which was the main reason, actually, why the LHC was built. And how is the Higgs detected in this experiment? So you would have two particle beams. The Higgs is produced here, but the Higgs is not a stable particle. It will decay. So it will decay immediately into, for example, two heavy Z bosons. So these are the particles that mediate the weak force, like radioactive decay, for example. And also, these particles are unstable. They will also decay to two pair of particles. So lepton, antilepton, for example, is an electron, and the antiparticle of the electron, which is the positron. So you can have 4 electrons in the final states. And if you sum up the momentum and the mass of this particle, you should end up with the original mass of the Higgs, because the energy must be conserved. So by tagging events in where you see, for example, 4 electrons and summing up momentum and mass, you end up with knowing what was the mass of the original particle from which the electrons came from. So this is how it looks in an animation here. You have the 2 protons coming. You have the 4 leptons coming out as white stripes. Plus, you have a lot of other particles which are coming from the debris of the proton. Okay? So that's the reason why we are having this very large data amounts, is that you have thousands of particles produced per each collisions, plus you're producing collision 40 million times per second. Clearly not storing all of those collisions on tape, because this would be larger than what we can possibly store. So we have to be selective. We are selecting only about 500 to 1,000 events per second that we store on tape. But yet, this is a very big data enterprise. And where are all this data going? The data, first of all, go into the CERN data center, where they are stored on tapes. Okay, because still, tape storage as persistent storage with low access is the cheapest solution. Okay, we use disks when we have interactive access to the data. And what you see here are robots, which are managing the tapes here. So whenever you want to have access to a given data set, you would do a query of your data, and the robot will fetch the right cartridge here. And at the data center at CERN, we have 40,000 cartridges in each library, and each cartridge is from 1 to 5.5 terabytes. So the total that we have right now is about 75 petabytes on tape. Okay? Altogether, also with the past experiments now, CERN has about 100 petabytes on tape. So, but since we want to go farther, this data center is not enough. So we realized that either we pull down some buildings at CERN and we make space for other buildings, or we go for another data center. But nowadays, the network connectivity is good enough to allow to take data here and store part of the data in Hungary, for example. So we have 2 dedicated 100 gigabyte per second links, redundant links that connect CERN with the Wigner. This is a new data center that will be in place for the upgrade of the LHC, which have part of the data shipped there. And so now you can imagine you have this huge amount of data. How do you really figure out where is the right event, where is the Higgs? How do you analyze the data? So we have a peculiar computing model that we have put in place for the analysis of the CERN data. And it's like an onion structure, if you want. So you start with data that are collected, as I said, at CERN, and they are also shipped in Hungary. This is what we call the tier 0. This is where the raw data of the experiments are residing. And then we have 13 tier 1 centers. These centers are now responsible for the processing of the data and the data reduction, exactly as your camera would go from raw data to JPEG, to make it simple, okay? So you need to reduce your data to a level that people can analyze on top of their laptops and home computers, okay? So, but is still, you see, these data centers are all around the world, not only in Europe, but also in USA and in Asia, so on. You have Taipei here. Plus, you have yet another level of data reduction, which is done by the tier 2 sites that are 160 sites all around the world. So in this diagram, as you go down, you go smaller in the data size per event. So here I've taken some figures of the measurements which we have done very recently. Now you see that Fermilab is the particle physics lab in Chicago. We can now ship data at 900 megabytes per second to Chicago. So it's an enormous rate. So you can basically take data at CERN, ship it 900 megabytes per second because we have, well, the trick is that we have dedicated optical links with the United States to do that. All right, so since I think I can recover because the other talk was shorter. So let me show you some data here to give you a feeling of what we are in terms of computing resources. So this is the number of, if you want, benchmark, of computing benchmark, if you want, as a function of the year. So I had to translate in something that you can understand.